Hello everyone. Myself Dr. Rajesh Prasad, working as professor in Computer Science and Engineering Department, AKGEC Ghaziabad. So today my presentation is on string matching algorithms. So as we know that what is string matching? So I'm going to focus four major algorithms in this lecture. So number one is naive algorithm, which we call it brute force approach. Sometimes this is also known as brute force approach. And second one is Knuth-Morris-Pratt KMP. And third algorithm in this string matching category is like string matching using finite automata. Definitely we are going to focus on the deterministic nature of the finite automata. Then last algorithm is going to be discussed. The one is Rabin-Karp algorithm. So what is string matching algorithm? What is string matching? As we know that string matching is basically a problem in computer science where our objective is to match a pattern inside a large body of the text. So this is actually there is similar problem of the searching. So question is that what is difference between searching and matching? So first search both looks similar, but there is difference. In the searching we used to get the first occurrence of the any pattern inside the text. Once we get it, we are going to return back. So in matching, we are not only interested in first occurrence, we are interested in all the occurrence of a pattern inside the text. For example, suppose we have a pattern, let's say A, B, C, A, B, right? And suppose we have a text, large body of text B, A, B, C, A, B, C, A, B, right? So in when we are using searching, so this pattern ABC is going to be found it over here, right? So in searching, this is going to return that okay, pattern is going pattern was found at this location. So it is not in searching, we are not interested in finding the further locations, right? While in matching, we are interested in finding all the other locations of the pattern inside the large body of text. So this is text, it can be images, it can be any kind of pattern and any kind of text. So let's have little bit application introduction. So text editing program, for example, we have seen that this is Microsoft Word, frequently need to find all occurrence of a pattern in the text. So those who have done editing in MS Word, right, and text like Notepad, there is big command. If you see Control plus F, this will give, this is the find command. So you can find out occurrence of a pattern inside any document, right? So same thing you can also do in the Notepad, but there is difference between algorithm behind MS Word and Notepad. See, so in Notepad we are text editor is not finding, not giving reporting the occurrences of the blank character. This will not report the occurrences of the blank character. For example, suppose we are given text like C, Ajay Kumar, right? Suppose we are given Ajay Kumar. Okay. So in and pattern is AY space then K. Suppose this is your pattern. So MS Word will find out this location of the pattern, while Notepad will say that this pattern is not going to be detected inside the body of the text. So that is the limitation of Notepad finding and MS Word finding. So this is very popular. We have so many algorithms. There is algorithm behind this searching. So typically the text is a document being edited and the pattern is a word need to be searched in the document. That is the idea behind text editing. So efficient algorithm for this problem is called string matching. It has many applications in, for example, in DNA searching, information retrieval, text editing. So many applications of the string matching are found in the literature. So so we have some terminology related to the string matching algorithm. So first I'm going to define valid shift. So this shift is going to be of two type, right? Shift is going to be of two type. First one is valid, right? And second one is going to be invalid. Okay. So what is valid shift and what is invalid shift? Any shift which is not valid is going to be classified in invalid category. So let's have some assumption that a text is going to be represented at 1 to n as an array, and pattern is also going to be represented from 1 to m, with limitation that length of this pattern is always less than or equal to length of the text. This is one limitation. Second one, that text element of text and pattern are taken from the some finite alphabet sigma, whose size is going to be denoted by sigma, right? See, for example, if you are taking pattern, let's say ABC AB, right? And text is also going to be taken from the same alphabet, say ABC AB and something like big one. So here sigma, we can see that generally sigma, this pattern and text are actually nothing but they are taken from ABC. Clear? So that means this is the sigma, its size is going to be 3. This is the notation in the string matching, number one. So yes, so and so what is valid shift? Any integer, we call it an integer, yes, is going to be valid if you can see ts plus 1, s plus 2, up to and so on, s plus m. M is the pattern length. This is going to be equal to pattern 1 to m. If you get any integer such that this equality is satisfied, then we call it yes as invalid shift. Otherwise, if this is not the case, this is going to be classified as invalid shift, right? Yeah. So actually, like this is one of the major objective to get the valid shift in the this finding. Okay, let's have an example. See, suppose this is the text ABC. This is going to be the one, and pattern is going to be ABAA. So you can see that this is detected at all the positions, like see these positions, all the characters are matching one by one. So that means this is 1, this is 2, numbering is 3. So shift is going to be 3. Why? Because if it is 3, that means text 3 plus 1, 3 plus 1, 3 plus 2, up to and so on, 3 plus 3, 3 plus 4. So that means T4, 4 to 7, T4 to 7, 1, 2, 3, yes, 4, 5, 6, 7, equal to pattern 1 to 4. We are always interested in this. That means yes is going to be valid shift, right? And other shifts, they are not going to be valid because we can't get ABAA in this matching. Okay. So this is the first terminology of the valid shifts. So there are many algorithms. First algorithm in this category is due to naive. This is known as brute force approach. Brute force approach. Brute force, that means like you can match just like a conventional method. See, so actually in this method we are just checking all the valid shifts. So let's see, suppose this is the pattern text, this is the text, right? Yeah, and this is the pattern. What will happen? We are trying s equal to 0, valid shift s equal to 0. So here this is equal, yes, but there is like a mismatch over here. A and C, they are not equal. So we discard further. We are not going ahead. So now let us try S equal to 1, right? So S equal to 1, that means after 1, this there is mismatch. We are going to discard it, right? So again, see, S equal to 2, there is matching. Yes, you can check it. That means this is going to be accepted. So S equal to 2 is going to be valid shift. Same thing here. See, there is match over here and there is mismatch over here, right? So that means this is not going to be valid shift. So only one shift is going to be detected, which is going to be the valid shift, right? So this is pseudocode of the algorithm. You can pass text and you can pass pattern. N is length of the text, M is length of the pattern. So as I said that you are going to check all the valid shift starting from 0 to N minus M. See what is here? What is N here? 2 to 4 to 6. This N is 6. Pattern length is 3. So M is 3. So 0 to, you are going to check 0 to 3. Yes, we have checked all the valid shift 0, then 1, then 2, then 3. So these valid shift are going to be checked actually. You cannot go beyond S equal to 3. So in the same situation, pattern, for every shift, you are going to check whether this is equal to pattern or not. If this is equal, then pattern occur with shift yes. Otherwise, far is going to be incremented automatically. See, like here, S equal to 0, G1, text 1 is okay, but text 2 is not okay. So that means S equal to 0 was discarded. Then again S equal to 1, we are checking it. Again S equal to 2, we got it. And S equal to 3, we discarded. So in order to look at this time complexity of this algorithm, so you can see that this is running N minus M plus 1 times, right? This is running N minus 1 times. And you know that if you want to check this whether pattern 1 to M is equal to this or not, so basically we are taking M comparison, right? M comparison, and within this like N minus M plus 1 time it is running. So its running time is of course N minus M plus 1 into M. Clear? So this is like N minus M plus 1. Of course, this is not like running time of this loop. Its running time is N minus M plus 2. But this is being tested like, this is being tested this time. But it's, since maximum, we are taking maximum. So, and this is running M time and it is body of the loop, and which is loop itself. So, we are going to get N minus M plus 1. So its running time is going to be this. So it is not necessary that pattern is going to be shifted from left to right. It's not like that. We can shift the pattern from right to left. Right to left is also possible. See, suppose same example, if we talk about AC, right, A, B, C, clear? Suppose we are talking about this, right? So you can shift from the right also. There is no problem. So, and this is your text, and pattern is AAB. You can shift right here. AAB. You can match. No, here, no, it's not matching. So that means this S equal to 3. Matching is now S equal to 3. This shift is going to be discarded. Answer is not going to be affected, right? So again, you know, you A, C, A, B, C, you can like see here again, S equal to, this is S equal to 2. Shift yes, this is equal, that means S equal to 2 is going to be valid shift. Okay, again A, C, A, B, C, then A, B, clear? So this is again going to be mismatched. So this is discarded. So S equal to 1 is again discarded, right? So next one is AC, AA, BC, then AAB. Again discarded. A is not equal to B, that means S equal to 0 is also not valid. So only one shift valid, which is S equal to 1. So this is the first algorithm. And we know that if we critically analyze the algorithm, and if number of pattern length is high, right? Suppose pattern length getting towards infinity. So in this situation, and n is already infinity, so this algorithm will be behaving like quadratic in nature. This will be like quadratic in nature. Yeah, quadratic. Okay. So that means this is not very much recommended in the literature, but it's okay. So second category, because of the naive algorithm was taking order of n almost n m into n minus m plus 1 time, which is almost quadratic. So this naive was not going to be recommended. So this another algorithm which is given by Knuth, Morris and Pratt. So this is actually algorithm is very good and its running time is linear in nature. So this is beautiful algorithm as compared to the naive algorithm. So that the time complexity of this algorithm is linear in the worst case, which is better. This is better than naive, of course. So what is problem with naive? Let's understand the problem with naive. Suppose you are working with comparison. Comparison is like say, and this is text, and suppose your pattern is A, B, like say D. Okay. So in this comparison, you are matching this, but there is a mismatch at this point. So that means all the efforts are useless. You have to restart from the second again. So this is one of the problem of the comparison. Second one, it is not counting the prefix and suffix, like say, suppose you have a text A, B, C, A, B and like C, A, B. Suppose we have a text like this, right? And suppose pattern is also A, B, C, A, B. If you look at the pattern, actually its certain suffix is also a prefix. Okay. So this suffix is also a prefix in the pattern. So definitely once you matched it, this information should be used in the matching, like see A, B, C, A, B. If you look at here, so you are done with the matching, and in naive algorithm, you have to compare one by one. Again, you have to compare one by one. So it is not intelligent. But on the other hand, this algorithm will take the information of suffix and prefix to match the pattern inside the text. So that is why it is like better than naive. And in this Knuth, Morris, Pratt, we are going to follow two steps. First one is pre-processing. This is important over here. Second one is the matching. Yes. So in pre-processing, pattern is going to be pre-processed, and after pre-processing, we can throw away the pattern. Pattern is not going to be needed further. And after pre-processing, you are matching that pattern inside the text. That is the steps. Yes. So in this pre-processing, like we are going to compute prefix function. As I said that this is going to take advantage of suffix and prefix. So important thing is that you have to compute the prefix function pi. So which stores the information about prefixes of a pattern. That is the beauty of the pi, prefix function pi. So what is prefix function? See, so suppose we are given a pattern of length 1 to m. Okay. So the prefix function for the pattern P is a map actually, which is mapping 1 to m to 0 to m minus 1. That is the prefix function. So this is mapping which map 1 to m, length m to 0 to m minus 1, right? Yeah. So how we are going to define actually? So you know this one, pi q is length of longest prefix of p. P is given here, right? So this is length of longest prefix of p. Prefix of p. We are taking prefix of p, which is proper suffix of pq. So let's have one question, then it will be clear. So suppose you have a pattern AB, AB, ACA, right? So it is clear that its length is 7. So see, like we have pattern AB, AB and ACA, right? This is the pattern, okay? Now, and we are interested in the pi I. We are interested in the pi I, right? So how to compute its prefix? How to compute? See, this is 1, this is 2, 3, 4, 5, 6, 7. Class, clear? So pi q, pi 1 means that length of longest prefix of p, which is proper suffix of pq. That means we are interested in proper suffix of p1. P1 means A. P1 means A. Its proper suffix is only epsilon. So definitely its length is 0 and which is going to be detected in the pattern. So it's going to be 0. Okay. Same thing if you look at the next point, this is AB. So if you look at the AB, its proper suffixes are only B and epsilon, right? Its proper suffixes. So you look at them, B is not a prefix of this pattern. B is not a prefix. So that means next prefix is going to be epsilon, which is going to be 0. Clear? Yes. So after this, like if you look at the P3, okay, P3 means ABA. Clear? Its proper suffixes are A, right? And then BA. Only two proper suffixes. So we are going to look into this in as a prefix, right? So BA is not found over here, no. Then A is going to be here. So that means A is here, 1. Clear? Yes. So next one is AB. So its proper suffixes are B, then AB, then BAB. Clear? And we can see that AB is the prefix over here. So we look into it and this is going to be 2. Its length is 2. So next one, if you look at here, so its proper suffix, look at here, yeah, it's up to this A, yes, 1. But ABA, proper suffix is ABA, which is also going to be the prefix of this, right? So that's why its length is going to be 3. Similarly, if you look at here, C is not prefix, so it's going to be 0. Then A, its length is 1, so this is going to be 1. So similarly, you can see that we can compute the proper prefix of the prefix function for this entire pattern. So this is the actually string matching algorithm, KMP. So in this you see that we are going to get length and pattern, and this is the computation of the prefix function. Once you get it, and Q is going to be 0. This is very simple. Like for I from 1 to n, you run the text into the pattern while Q greater than 0. This value, if it is greater than 0 and you got that PQ plus 1 is not equal to TI, Q is going to be reset by pi Q, right? Yes. If PQ plus 1 equal to TI, keep increasing Q. If q equal to pattern right length, then pattern occur with shift I minus 1 and always reset q by pi q. So this is, you can see that computation of prefix function is linear, and this algorithm is also running linear. Its running time is going to be linear in nature. So thank you. So these are the references. You can check Thomas Corman last string matching algorithm is the topic in this, and another book is Alfred Aho. So thank you.